Hello everyone, welcome back, and I hope all of you are doing good. After a very long time, we are here with our another lecture. So, before starting with our lecture, let me just give you a few of the things that we already did for this numerical methods with Python course. So, as all of you know, that we have already completed our module 1, where I told all of you that in our module 1 we will be talking about the basic things in Python, right? Okay, so in our module 1 we have covered a lot of basic things about Python. So I told you about the syntax. Basically it was all about the syntax, and obviously to give you people few things which, like, all those students who were completely beginners and they do not have any idea about the Python language, so it was very important to tell few of the basic things as well as how to write those basic things that was called as the syntax. So we have covered a lot of things like operators, then a lot of functions, and then loop. So and functions also we covered, but function, because of some technical issue we couldn't complete the function part, but don't worry, that will come again because I have to cover few more things for this course. So I'll be taking the function class again, so don't worry about it. So we have talked a lot of things about module 1, and like for few days I was not posting any video, or I was not taking any live class because I wanted you people to revise few of the things or to get familiar with all those things, because most of the students were watching the recording classes. So I wanted them to finish with their recording so that by the time we are ready for our module 2, you people have completed our module 1, where we have covered the Python for, obviously, for absolute beginners. Okay, but now we are at the stage where we can start with our module 2, or basically if we say that, our numerical methods. Okay, so we have to start with our numerical methods today. But before starting with it, I would like to tell you a few more things that how we are going to proceed with our module 2, since it is a very important module and this is going to affect your whole life, whole career, because if you get interested in this part, then all those students who are enrolling in masters or who are already enrolled in masters and they would be doing their projects. So if you got interest in this field, then your whole higher study research career is going to be based on it. Okay, so that's why we would be going a little slow about it, and we would understand everything step by step. All right, but before that, let me just tell you one more thing, that how I'm going to continue with this module 2. So for this module 2, I am going to cover this in two parts. So first one is going to be the theoretical part. Okay, because without covering the theory I cannot go for the like coding part, okay, in Python. So you should understand the theory first, and then we will go for the coding of that particular thing. Okay, so what I will do, I am going to create two playlists. For initially we are going to understand this thing, and then today itself I am going to start with this course. Okay, so no need to like panic. Okay, in this session I'm only just going to introduce how I'm going to carry on with this course. No, I am going to start this course today itself, and today we'll do one method, and then we will take another. Okay, so I'm going to create two playlists for this module 2 itself. In our these two playlists, one of the playlist would be for the theory portion and one of the playlist would be for the coding portion. Okay, for example, today if I am going to cover Gauss elimination method. Okay, so since most of you already familiar with the Gauss elimination method, but still there are some graduation students also, like for those who are doing their bachelors, they are also watching this video, so they might not be familiar with the theoretical part. So in first video, that is the first lecture that you would get, is going to be the theoretical explanation. Okay, it is going to be like theoretical explanation for the what, for the Gauss elimination, and the second one is going to be the coding portion for what I covered in our theoretical lecture. But there is a catch. Okay, you cannot miss this theoretical lecture. All those like who are enrolled in masters or who are already planning to enroll in masters, you might have already covered Gauss elimination method, so you would be thinking, okay, I can skip this theoretical part and I would directly go to the coding part. Then it is a mistake, and here is a catch for all of you, that in this theoretical session, I am not only going to tell you, okay, how this Gauss elimination works. I will tell you the Gauss elimination as well as I am going to tell you the algorithm. I hope all of you know what this algorithm means. Algorithm means how you are going to make your system, your computer understand that this is a Gauss elimination method. So algorithm for what? Algorithm for creating the program for the Gauss elimination method. For example, if we are doing Gauss elimination. Okay, so you cannot miss this. And if I'm not wrong, all of you are mathematics students, or even if you are not engineering student or any student who is sitting here, if you have read about the Gauss elimination method, then I think you might have studied only this much, that there are these suppose n number of equations with m number of unknowns or whatever, then you have to solve this system. So you applied that method mathematically and you got the answer, right? That whether the solution exists or not, and if it exists, it is this, right? But we are not going to do only this much. Okay, things are not limited to solving only system of linear equation. We do have to understand few of the things which are quite important. Okay, and in the meantime, when this course will progress, you will understand that how much important this module 2 is. Okay, once we will do few methods, and then I'm going to talk about few of the physical problems that you do solve in few of your projects. You will understand most of the physical problems got ended by turning into a, or by they most of the physical problems they finished by converting themselves into a system of linear equation. And if you are well familiar with solving system of linear equations, then it would be very easy for you to tackle that problem. Okay, so this is what I wanted to tell you, that how we are going to work in this course. So like for one of the method, you are going to get two videos. Okay, the first one is going to be the theoretical explanation of that method along with the algorithm to create the code. And in the second video, you are going to get how to create the program or how to code that particular method in Python. Okay, so this is how we are going to proceed. So there would be two playlists made for this module and you have to follow them one by one. So one day, one video would be added in one playlist and the another day it would be on the second playlist. And in 1 week you may accept 3 videos. Okay, I'm already telling you that I'm not going to post every day, and the classes are also not going to be live for now, but maybe I can take live. So this is not a like a thing which is going to be fixed. I may take a live class if I want. So I will try to give you 3 videos or 3 classes per week for this module 2, because it is very important for you to understand everything step by step. All right. I hope till this point everything is clear to all of you. So now let's proceed with this module 2. So in our module 2, the first thing that we are going to cover, or you can say the first topic that we are going to cover, is our system of linear equation. Okay, so as I already told you that in our projects that you would be doing in your masters or even in your PhD, or those who are doing or those who are planning to do their PhDs, they would know that you would be obviously given a physical problem, right, which you can solve. So you will see that most of the physical problems being after a particular operations, they ended up by converting into a system of linear equations. So if you know how to solve a system of linear equation, it becomes easy for you to tackle that. As I already told you, that is why we are studying system of linear equations. And what else are the benefits for this, I am going to tell you later once we will proceed and we will advance in this course. All right. So since I'm expecting most of the audience here is a mathematician, so I'm going to tell you that how our system looks like when we are dealing with only n number of unknowns. Okay, I'm already telling you that right now what we are doing, we are dealing with n number of unknowns, that is our unknown vector or unknown column you say, and we are dealing with n number of equations only. Okay? So our system of linear equation is going to look like a n cross n system of linear equation. All right. So as most of you have already solved a lot of questions, yeah, in your courses, in specifically in linear algebra, if I talk about, you might have gone through a lot of system of linear equations. So if I want to write them, so they are going to look like this: a11 x1 plus a12 x2 up to what, a1n xn, right? And then since we are going to talk about the not only the homogeneous, obviously also the non-homogeneous one, so we are going to consider a general system of linear equation, that is b1. And then here we have a21 x1 plus a22 x2. In a similar way, here we have a2n xn is equals to b2. And since I told you that we have n number of equations, so we will be having n number of rows. So this is an1 x1 plus an2 x2, and now it ended up where ann xn is equals to bn, right? This is how our system looks like. Or if I told you that we have n number of linear equations, because system it what? A collection of more than one simultaneous equations is a system of linear equations. Okay, so this is how our n cross n system looks like. So where if I say that these aij's, okay, these aij's are what? These aij's are the coefficients, right? And simply if I'm going to write it, these are the coefficients. And these bj's are what? These are the constants. And what about this xi? This xi is simply what? It represents the unknowns. All right. So if you see that we can also write, and I don't think so there should be any problem for all of you, especially for all those mathematics students. In short, we can also write it like this, in form of a matrix form. So a21, a22, then we have a2n here, and similarly we have an1, and this is an2, and then we have ann, right? This is how our system looks like. And here x1, x2 up to what? Xn, and this is going to be our what? B1, B2 up to Bn, right? So you can see here is a n cross n matrix. This is a n cross 1 column vector, which is a unknown column vector, and this is what? This is also n cross 1. Okay. So this became very simple now, and I already told you that aij's are the coefficients, and in a similar way bj are the constants. And what kind of constants they are? They are already known to us. And then what if I talk about xi? Xi are the unknowns. Okay, xi are the unknowns. So this is how it looks like. So to write it in a very simple form, and so that it becomes easy and we don't have to write it again and again, we converted into matrix form. So we wrote it like this: ax is equals to b. Okay. So in like we are doing it purposely, okay, because this representation is going to be useful for computational purposes. So that is why we wrote it like this, because for computational purposes it is going to help us in this way. We are going to write a augmented matrix, and sometimes we also call it augmented coefficient matrix, and we write it like this: a11, a12, and then we have a1n, and we create a dotted line, and we also consider this known column vector also. So this is a21, then a22, this is a2n, then this is b2, and then finally we have an1, an2, and ann, and this is bn, right? So this is, we call it simply coefficient augmented coefficient matrix. Okay, or you can simply call it augmented matrix. There is no problem. Since our A matrix, it is called as coefficient matrix, is involved in this matrix, so we are calling it as augmented coefficient matrix, or simply you can call it augmented matrix. So for computational purposes, this particular representation of the equations is used. Okay, and then we will see how it works. Since most of you are already familiar with it, so that's why I am just speeding up in this one, and then we'll go slowly for the one that we don't have any idea about. Okay, and then let's talk something about the kind of a solution. Okay, so we most of the things depends on the coefficient matrix. Okay, if I am writing it ax is equals to b. Okay, we are talking in a very general way. We are not going in a kind of a thing that we usually do in mathematics. There is a whole chapter on system of linear equation, and we do solve it. We go for consistent, inconsistent solution and all that, then homogeneous, non-homogeneous. We are just doing it in a more general way. Okay, we are not going into the particular cases. All right, so we basically create two cases over here. We calculate the determinant. Okay, if the determinant is 0, we call that A is a singular matrix. Okay, we call it A is a singular matrix. And in case, what happens in case the determinant of this coefficient matrix is non-zero, so we call it A is a non-singular matrix. A is a non-singular matrix. And what happens is that in this case, when the determinant of the A matrix is non-zero, we always say that we have a unique solution. Unique solution means the only column vector x that exists and that satisfies all these n number of equations is only one vector. There is no other vector other than x which can satisfy all these equations. Okay, so unique solution means only one solution. And in this case, we can also say none of the row is the linear combination of the other rows, or we can say none of the row is a linear combination of, none of the column is the linear combination of the other column. Okay, so we already are familiar with all these things. We have gone through our linear algebra course in a very detailed way, so we know that. Okay, we also connect it. Okay, that means all of the rows are independent, or we can say all of the columns are independent. None of them is a linear combination of the other. So this case is pretty much simple, that you just have to evaluate the determinant of A. And why we are doing all this, there is a topic which is called as ill conditioning. So we'll talk about it, not today, but some other day when we are going to require that ill conditioning topic 1. So we'll study, but for now, since we are dealing it, so I'm telling you right away. Okay. Now, if the determinant of A is 0, so it means that you can have either no solution, or you can have infinitely many solutions, right? You can have no solution, or you can have infinitely many solutions. So this case, we will see how we get all these kind of things in coding it, and it's going to be quite interesting for all of you, let me tell you. Because this is just a theory class, so you are seeing, okay, and you already know in mathematics how do we do it, but in a language of system you are going to enjoy, okay, how beautifully this works. So in this determinant of A is equal to 0, either the system will have a solution and those are going to be infinitely many, or otherwise the system is not going to have any solution. That means there does not exist any x vector which satisfy all the equations. All right, so this is, and if you want to take an example for it, so, and since it's easy, all of you can already predict it. Here, suppose we have 2x plus y is equals to 3, and then 4x plus 2y is equal to 0. Okay, so this is a system because you have more than one equation and those are simultaneous equations. So you see, if you multiply this equation by 2 and if you subtract it, so you are getting 0 is equal to kind of a 6. So this system, which is absurd in mathematics, right? So this system has no solution. All right. In a similar way, if I take one more example, suppose I am writing 2x plus y is equals to 3, and then I am writing 4x plus 2y is equals to 6. Okay, and if you see here, if I want to evaluate the determinant of the coefficient matrix 2 1 4 2, how I got to know, okay, that it goes to the category of no solution or infinitely. So see here, the determinant is 4 minus 4. Okay, 4 minus 4, it's 0. So I got to know, okay, this system cannot have unique solution for sure. It cannot have unique solution. So either it goes to no solution or it goes to infinitely many. And how I got to know? I multiplied the second equation by 2 and then I subtracted. So 4x minus 4x, it vanished, and then 4y minus 4y vanished, and then it is going to be 6 is equal to 0, which is absolutely absurd, right? So that's why I got to know, okay, there does not exist any x and any y for which it satisfies both the equation. And for this one again, our A matrix is 2 1 4 2, determinant is again 0. But now if you see here, there are infinitely many solutions. And how I got to know? I multiply this equation by 2 and you see they both are same. Okay. So there exist infinitely many possible values for x and y which satisfy both the equations. Alright. I hope it's fine for all of you. And those who have already studied from me linear algebra, and even if you, all of you, those who haven't watched and they want to watch system of linear equation, so I have already taught you people system of linear equation, and they might be in the course of linear algebra. There is a playlist, if you want you can watch it. So I've also told you about the geometrical interpretation about it. You see there are going to be like two parallel lines. Okay, and so then parallel lines and then there would be a case of overlapping lines, right? So you are going to see all those things from there. So please watch it if you don't have any idea. But since it is not too much required, it's just that if you want to get a great knowledge about this one, how these equations work and what does it mean in geometrically, that is why I'm telling you. Otherwise, even if you do not watch, it's fine for this course. Okay, I'm just giving you a uh, an idea about those who don't have about how system work, or those who just wanted to have a recap. Okay, so we understood how the system of linear equation looks like. Then we have gone through another way of writing it down. Ax is equals to b in matrix form. Then we got to know about our augmented matrix, and then depending upon the determinant of this value a, how we can got to know, okay, what kind of solution this system is going to have. And obviously for determinant a equal to 0, you have to verify by solving or by understanding the equations. All right, so this was everything about the basic things for system of linear equation. Okay, so if I would tell you that if you have any doubt in any of the things that I am teaching you right now, you can just drop a comment in the comment section and I'm going to reply to that. Okay, so coming to the agenda for today that we have to see for what I have scheduled this class. So we have to deal in this chapter, that is system of linear equation specifically, we have to talk about the methods. Okay, and what kind of methods? Methods of solution. And from here the very crucial and the very important topic starts. So, and since the name of this course is also numerical methods, so obviously we have now come to that part, which is the methods of solution. And since we are dealing with system of linear equation, so we are interested in the methods for finding out the solution of system of linear equation. Okay, so let me tell you, and I'm going to write it in such a way that it's very useful for you, and it's kind of a short note. So if you want to revise for coming to the next class, it's easy for you. So we have two classes. Okay, I'm going to write everything for you. So we have two classes of methods for solving the system of linear and algebraic equations, and this is for both. Okay, two classes of methods for what? For system, for solving systems of linear and algebraic. Okay, But here we are dealing with linear. So I'm going to tell you that linear algebraic equations. But here we are focusing upon what? Linear. Okay. So, and those are what? Those are direct. There is a method called as direct method, and there is a method which is called as iterative method. Okay. Direct method and iterative method. So we will see all of them one by one. As I told you, we'll have to do a lot of things and we have to go in a long run. So we'll see all of them one by one. Okay. So we have two classes of methods. The first one is the direct method and the second one is the iterative method. So the basic difference about the direct method and the iterative method is that, okay, let me write it down here itself. So if I talk about direct method, so the common characteristic of direct method is that, listen to me what I am saying, this is a very important thing, that the common characteristic of direct method is that they transform the original equations into equivalent equations. Let me write it down for you. So what I said right now, that the direct methods, they transform, okay, they transform what? They transform original equations into equivalent equations. And what are those equivalent equations? We will see. And I'm going to tell you right now, equivalent equations. Okay. So equivalent equations are what equations? So simply if I want to say that equivalent equations are those equations that have the same solution. Okay. Equations that have same solution. That have same solution. So in short, I hope now you are understanding what I am trying to say. Direct methods are methods which do not evaluate directly the solution of the original equations that are given. Direct methods are those methods where the process is that we will convert our original equations into equivalent equations. And what are those equivalent equations? That have the same solution. And why we are doing this? Because it makes our job easier to find out the solution. Okay, because because it is not, sometimes it's not easy to evaluate the solution with the help of original equation. So we convert them into the one which are easy for us to evaluate. Okay, so we convert them into equivalent equations, and equivalent equations are those equations which have the same solution as that of original equation. Okay, and now the question is, how do we transform our original equations to equivalent equation? And this is why I told you that you know how to solve Gauss elimination, you know how to solve value decomposition, whatever. But these are the things that you do not know. Okay, and it is important for you because this is where the algorithm is hidden, and this is where the what do we say, the base of the method is. Okay, so the direct methods are those methods which transform original equations into the equivalent equations. And now the question is, how does this transformation works? So this transformation is carried out by three operations. Okay, there's transformation of converting our original equations into equivalent equation is done by three operations, and we call these three operations as our what? Elementary operations. All right, these are called as elementary operations. And these elementary operations do what? They do not change the solution. Okay, they do not change the solution. So I hope now you can connect it with the first point that I have written, that if when we are going to apply the elementary operation, obviously our equations are going to change. That is, the coefficients of the variables are not going to be the original ones, they are going to change. So those would be called as equivalent equations. And now the system of equivalent equations that we'll have is going to have the same solution because the elementary operations do not change the solution. Okay, and how this happens, again you can see the three elementary operations that we have is exchanging our two rows, right? We exchange two rows. Suppose we exchange R1 by R3. So the first row is going to be R3 and the third row is going to be R1. And you know that in this case, determinant only changes by the negative sign, right? Changes sign of determinant of A. Am I right? It only changes the sign. So it's easy, right? If determinant A is non-zero, then it is going to be non-zero. So we will have unique solution. Even if we exchange two rows, only the sign is going to change. Okay. Then our next one is that multiplying an equation by a non-zero constant. Right? So multiplying by a non-zero constant in any equation. Alright, in any equation. So if I am going to multiply our ith row by lambda, so what will happen to the determinant? Determinant is also going to be multiplied by lambda. So if it is non-zero, it is going to be non-zero again. Alright. And the third elementary row operation, I'm writing it in a very short way because all of you are already familiar with these kind of things. But if you didn't understand anything, please let me know in the comment section, okay? And second, the last one is very important for you, which I am going to write for sure. That is multiplying an equation by non-zero constant, and then it is going to subtract, then subtracting it from another equation. And in this case, determinant of the matrix A is unchanged. All right. So I hope now you have understood about the direct methods. Simply, they transform the original equations into equivalent equations. And what are the equivalent equations? It is also a very good topic to be discussed, but right now it's not needed. So I've just told you that what it simply means. So equations that have the same solution as that of original equations. And how this transformation goes? This transformation is done by using three operations that are called as elementary operation. The first one is if we exchange two rows. Second one is if we multiply any equation by a non-zero constant. And the third elementary operation is that if we multiply an equation by a non-zero constant and then we subtract it from another equation. And in all these cases, in first one, only the determinant changes by negative sign. Second one, determinant multiplied by that non-zero constant. Third one, determinant remains unchanged. And that's how our solution remains unchanged even after converting original equations to the equivalent equations. Okay, these are the few things about the direct method. Now, another thing is, let's also talk about iterative method. What are the iterative methods? So if I talk about iterative methods, the basic difference is that direct method converts our original equations into the equivalent equations. But in case of iterative methods, and we also call them indirect methods, okay? So don't get confused. This is also called as indirect methods. Okay? So indirect method, what do? They start with a guess. Okay, they start with a guess of solution X. Like there is a system of linear equation and I assumed already without evaluating, I assumed, okay, this X is the solution. Okay. So now what we are going to do, I am going to repeatedly, okay, I am going to repeatedly refine my solution. Because for example, suppose my solution is x is equals to 2. But मुझे तो ये बात नहीं पता है ना स्टार्टिंग में, क्योंकि मैंने तो सोल्यूशन इवैल्यूएट नहीं किया है. तो ये मेथड क्या कहता है, ये अज्यूम करेगा स्टार्टिंग में कि ये जिसको हम इनिशियल सोल्यूशन कहते हैं, हम अज्यूम कर लेंगे कि ये मेरा है. सपोज मैंने मान लिया कि x इज इक्वल टू 0 इज द सोल्यूशन. तो अब हम क्या करेंगे, हम इस सोल्यूशन को रिफाइन करेंगे बार बार. अगेन एंड अगेन वी आर गोइंग टू रिफाइन. सपोज एक बारी में x 0.5 पहुंच गया, फिर x इज इक्वल्स टू सपोज 0.8 पहुंचा, फिर मान लो 1.2 पहुंच गया, बट अभी भी हम सोल्यूशन से बहुत दूर हैं. तो हम इसको रिफाइन कर रहे हैं. दिस प्रोसेस इज कॉल्ड एज द रिफाइनमेंट ऑफ आवर सोल्यूशन. और जब तक हम 2 के पास नहीं पहुंचेंगे, वी आर गोइंग टू कंटिन्यू दिस प्रोसेस. अब नाउ द क्वेश्चन फ्रॉम योर साइड शुड बी दैट हाउ वी आर गोइंग टू रिफाइन इट, राइट. एंड कैसे हमको पता चल रहा है कि 0.5 सोल्यूशन नहीं और हमें आगे बढ़ना है. ओके, सो फॉर दैट वी हैव अ कन्वर्जेंस क्राइटेरिया. जब हम आइटरेटिव मेथड्स पढ़ेंगे देन वी विल सी इट वन बाय वन. ओके, we have some convergence criteria. So what we have to do, we are going to repeatedly refine our solution until a certain convergence criteria is reached. Okay, until a certain convergence criteria is reached. तो होगा क्या, x is equal to 0 लिया, रिफाइन किया, 0.5 आया, फिर हमने कन्वर्जेंस क्राइटेरिया से चेक किया, ओके वो मैच नहीं हुआ, हमने फिर से रिफाइन किया, 0.8 आया, फिर कन्वर्जेंस क्राइटेरिया से मैच किया, नहीं मैच हुआ, अगेन वी रिफाइंड इट. Okay, so that's how the iterative methods work, that we start with a guess of the solution x and then we repeatedly refine the solution until a certain convergence criteria is reached. Okay, that is why iterative methods are generally less efficient than their direct counterparts due to the large number of iterations. Okay, so that is why what we do most of the times we do use direct methods, but ऐसा नहीं है कि आइटरेटिव मेथड जो है वो हमारे पास लेस एफिशिएंट है क्योंकि लार्ज नंबर ऑफ आइटरेशंस लगती है तो वो सिग्निफिकेंट नहीं है. नो, दे डू हैव अ सिग्निफिकेंट कंप्यूटेशनल एडवांटेज, बट in what cases we will see, because that depends on our coefficient matrix and some things called as sparsity and everything, so we will see that later. But for now it was important for me to make you people understand that there are two classes for methods for finding out the solution of a system of linear equation or algebraic. They are direct and iterative, but here we are studying about the linear system of linear equation. Okay, so direct methods are those methods which transform the original equations to the equivalent equation and then they find out their solution. And iterative methods are the methods which start with a guess and then they repeatedly refine the solution until that convergence criteria is reached. Okay, I hope it's fine for now. And then what's next is that we are going to see about the direct methods. Okay, direct methods. And direct methods for what? Direct methods for system of linear equation, or I should write it down, for solving system of linear equation. All right, this SOL simply means system of linear equation. So what kind of direct methods you all have studied, you can comment it down. But let me tell you that there are 3 popular direct methods, each of which uses the elementary operations that I already told you to produce its own final form of easy to solve solutions. Okay, so let me write it down in a way which is easier for you to understand. So we have method and there is an initial form that I told you, ax is equals to b, and the final form, like how this method works. Okay, so the first method that we have is what is Gauss elimination method. Okay, we have a Gauss elimination method, and our system, as I already told you, it's in form of ax is equal to b. But we are studying what? Direct methods. So I already told you what direct methods do. They transform our original equations into a equivalent equations by using elementary operations. So initial form is this, but once we transform into equivalent equation, it takes the form of ux is equal to c, where this u is a upper triangular matrix. Okay, so our matrix A is converted into a upper triangular matrix U for easier calculation. Okay, then our second method is LU decomposition. Okay, we have LU decomposition method as well, and this again we have ax is equals to b, but LU decomposition method transforms the equivalent, it transforms into equivalent equations that took the form LUX is equals to C, or sorry, it should be B. Okay, So we will see how it works. And the third one is Gauss-Jordan elimination. Okay, this is Gauss-Jordan elimination. And again, Ax is equals to B, and we convert it into the form Ix is equal to C. Alright. So this U is a upper triangular matrix. Upper triangular matrix. Then this L is a lower triangular matrix. And this I is what? This I is a n cross n identity matrix, because we are right now dealing with n cross n system of linear equations. Okay, this is identity matrix. So I hope now you can connect with the direct method that I told you, that they transformed our original equations into the equivalent equations. But don't worry, even if you are not able to connect it for now, I am going to tell you everything in detail. And today's lecture is little bit long. You can say it's taking a little more time, because I have to explain you everything in from basics, right? But from tomorrow onwards, it's not going to be too much long, because I just have to explain you the method. And you already understood what is system, what are direct methods, what are indirect methods, okay? Or iterative methods, whatever do you call them. So let's understand few more things. As I told you that Ax is equals to B is being converted into Ux is equals to C in case of Gauss elimination, right? Okay. In case of Gauss elimination. So let me just connect you people to how this is a direct method, okay? And I told you that it is direct method, so it transforms. So let me tell you how it converts. So our system was A11 x1 A12 x2, okay? So you can simply see here A11 x1, okay? Let me write it down in system form only. A11 A12, and then here we have A1n, okay, and in a similar way A21 A21, and then we can write it into the matrix form. And all of you already know how our upper triangular matrix looks like, okay? I hope everybody knows it. So this is U11, then 0 0. Oh, just give me a moment. This is an upper triangular. So U11, U12, U13, and it is going to take n cross n matrix. But for example, I'm telling you for 3 cross 3, how does it look? Then U22, U23, and 0 0 and U33. That means all the elements below the diagonals are 0. Then that matrix is considered to be the upper triangular matrix. Okay, that's how it looks like. Then I told you that Ax is equals to B takes the form Lux, right? Just now I told you Lux is equals to B. So in this case, this is our LU decomposition. So in this case, this L matrix is a lower triangular matrix. So L11, then 0 0, then this is L21, L22 0, then L21, sorry, L31, L32, L33. Okay, so that's how our lower triangular matrix look like. I hope it is okay for everyone. And identity matrix you already know. Okay, this is 1 0 0, then 0 1 0 0 0 1. We don't have to talk too much about it, because everybody knows about the identity matrix. All right. Now the question is why we are doing so. Why we are converting from this form to this form. Why we are converting from this form to this form, or why the direct method transforms the original equations to the what equivalent equations. Why we are doing so. So I told you one simple reason: to make the computations easier, right? There is only one reason: to make the computations easier, to get to the solutions in an easy way. So how it happens is that this Ax is equals to B. How it looks like if I'm going to write it in form of equation: A11 x1 plus A12 x2. This is A1n xn is equals to B1, right? And for example, let's take n is equals to 3, okay? Just to make you people understand easy way, n is equal to 3. So Ax is equals to B looks like what? A11 x1 plus A12 x2 plus a1n xn is x, because we took 3. So this is a13x3 is equals to b1. Then we have b21. So sorry. This is a21x1 plus a22x2 plus a23x3 is equal to b2. Then we have a31x1 plus a32x2 plus a33x3 is equal to b3, right? And you don't have any idea about how to solve it, because it's very difficult. Now if I say that you converted it into what? By applying Gauss elimination method, you converted into equivalent equations. And what are those equivalent equations? Or simply if I talk about the form, it is simply ux is equals to c. And since you know how this u looks like, this looks like u11, u12, u13, then 0, this is u22, u23, then 0, 0, u33. So if you are going to write again and solve this ux is equal to c, how it will become? u11x1 plus u12x2 plus u13x3 is equals to c1. Next equation, u22x2 plus u23x3 is equals to C2. Next, u33x3 is equals to C3. And as I'm going to give you one example, you will see that from reaching this equation to this remains same. Okay, then from reaching from this equation to this equation, you used nothing but elementary row operations. From here to here, you used elementary operations. Okay. You used what? You used elementary operations. I'm simply writing EO. And again from this to this, you used elementary operations. So these are the equivalent equation. Okay. This equation A, equation B and equation C are called as the equivalent equations to the equations that are original equations. Okay. And they have the same solution as of these original equations. Now you see, it was very difficult to compute our solution from these three equations, but it is very easy to compute our solution from these three equations. And how we can calculate it? It is called as back substitution, that all of you already know. This is back substitution. So the Gauss elimination method uses back substitution. How? From here, we evaluated x3 is equal to c3 by u33. Right? This is this. If our u33 is non-zero. And those are the things that you can understand, obviously. Right? And now we will go back. How? Why this is called as back substitution method? Because we are going back into this direction. Because now we evaluated x3 and from this equation we can evaluate our x2. How? C2 minus, then you have u23 and you can put the value of x3 as c3 by u33 and divide whole thing by u22, right? So you are going in a backward direction. That is what it is called as back substitution. You are substituting the values in the backward direction to find out the rest of the unknowns. So these are called as the equivalent equations because they do have the same solution as these three original equations have. But it was very difficult to compute our solution from three equations. So Gauss elimination is a direct method. We convert the original equations to the equivalent using elementary operations and then it evaluates the solution. Okay, I hope it's clear. In a similar way, we have a11x1 plus a12x2 plus a13x3 is equals to b1 and we have a21x1 plus a22x2 plus a23x3 is equals to b2. Then we have a31x1 plus a32x2 plus a33x3 is equals to b3. This is our ax is equals to b. Okay. Now if I use what? If I use our LU decomposition, for example, LU decomposition. Okay? So LU decomposition does what? So it converts into LUX is equals to B, right? So in this method, you have to go by two methods. How does it go? It simply solves for Ly is equals to B, and from Ly is equal to B, you get your Y, and after that, what do? You use Ux is equals to Y. So from that, you evaluate your X. So first you evaluate, because your L is known, right? Because you have to write A is equals to LU. So you evaluate this L and you evaluate this U. Then you first solve Ly is equals to B, because L is known now and B is known. So you can simply evaluate Y, and now you can use this Y here. This is your second method to solve. U is known, Y is known, and you can find out X. So are you realizing what's happening? You have converted this Ax is equals to B into this by using, and again solving this is what? Converting the original equations into the equivalent equations to get the solution. But there is a catch over here. And what is the catch? That Ly is equals to B. Okay, this Ly is equals to B. How does it look like? If I want to see, this is L11Y1 plus L12Y2 plus this is not going to happen. Why? Why? Because our lower triangular matrix looks like what? L1100, L21, L2200, L31, L32, L33. So now you see L11Y1 is equals to what? B1. Then L21Y1 plus L22Y2 is equals to B2. So are you realizing something? That in this LU decomposition one, Ly is equals to B uses forward substitution. Yes, because from here you got your Y1 and then you went into this direction. From here you will get Y2 and then from here you will get your Y3. So this one uses forward substitution, and finally Ux is equals to Y uses back substitution again. And all this is what? This is the direct method, because you are converting your original equations into the equivalent equations, or the equations that have the same solution to as that of original equations. Okay, this is the logic behind everything, and this is how it goes. All right, now I think everything is fine with us. So in today's lecture, what we are going to do, we have to understand about the Gauss elimination method, but I think it's more than enough for today. So we have to understand Gauss elimination method. So the next lecture that you are going to get is going to be Gauss elimination and its algorithm. It's not going to take a lot of time. It's simply our 30 minutes lecture, or even more than 30 minutes. And then second lecture you are going to get on its code or its program. Okay. So that's it for today. Again, I'm telling you, if there are any questions, please do let me know in the comment section. So what we covered today was what? Was methods to solve. And I also told you about how this module is going to work. So there would be two playlists, one for the theoretical explanation, second for its particular program. Then I told you what how does the system looks like. Then it's another representation in form of Ax is equals to B. And then we saw that Ax is equals to B solution depends on the determinant. And then we saw some examples. Methods, two classes, direct and the indirect. We understood about direct and indirect. Then we gone through the direct methods for solving system of linear equation, and those are three methods that we are going to study. And we just connected that how this Gauss elimination and LU decomposition, even if the Gauss Jordan is how these are the direct ones. Okay, so just to link you how we are converting our original equations to the equivalent equation. All right, so that's it for today. This was our first lecture on module 2. Please see this very carefully, because if you didn't understand initial 2-3 lectures, then it won't be easy for you to cover this course and be with us till the ending of this course. Okay, so if you have any problem, any question, please let me know. Okay, so thank you so much. and please provide your feedback for this class, and we'll meet again in our next class with the Gauss elimination and its algorithm. Till then, bye bye, take care and keep studying.